All right, I'm sorry guys, there's slides here. Just saying, with data. Okay, so climate change calls for urgent innovative solutions, particularly in the cooling industry, which contributes significantly to greenhouse gas emissions. As the demand for cooling increases with a warming world and populations continuing to grow, the search for sustainable technologies is more important than ever. Here comes the magnetic refrigeration. Magnetic refrigeration promises efficient cooling without the detrimental environmental impacts of commercial refrigeration. At the heart of the magnetic refrigerator lies the magnetocaloric material. This leverages the quantum property known as spin. And so we have this nice diagram up here. So we can think of the electrons acting as sort of mini magnets in the material. We apply a field and we align those magnets with each other, and what we do is decrease something known as the magnetic spin. Since we're doing this in a system that's adiabatic, so the total entropy of the system must stay constant, the lattice actually counteracts this decrease in magnetic entropy by increasing its own entropy. And it does this by vibrating its atoms, and so the material becomes hotter. If we do this the other way around, by taking away the field, we randomize those spins with respect to each other, as you can see up there. And what we do is we increase the magnetic entropy, and so the lattice decreases its own entropy and the material cools down. So through this unique interplay between magnetic entropy and lattice entropy, we're able to control the heating and cooling of the material. So ferromagnets, which are materials that have a magnetic moment even after we remove the magnetic field, are of particular interest in this area as they exhibit some very large change in magnetization at something called the Curie temperature. And this is the temperature at which they go from that ferromagnetic state, where they have an overall magnetic moment, to a paramagnetic state, where they don't have an overall magnetic moment. And so the Curie temperature would then correspond to the temperature we run this cycle at. Ideally, that would be around room temperature, which is about 300 Kelvin. So all we have to do is apply a small permanent magnet, and we can kind of probe that transition and get that impact. So my initial work looked at a ferromagnetic first-order magnetocaloric material, mouthful, comprised of lanthanum, iron, and silicon. It had a Curie temperature of around 200 Kelvin, so a little bit low for room temperature applications. But what I was able to do was replace some of the iron with cobalt, and what I saw there is that I could get a positive linear trend, as you can see here, of Curie temperature with cobalt concentration. I even managed to get it all the way up to 360 Kelvin, which is super cool. That's not a pun. And then from there, we come across the idea of, well, what do I mean by order? Okay, well, it's a bit of a complicated issue, but all you need to know for this talk is a first-order material exhibits a large change in magnetization at a certain temperature, called the Curie temperature, as already mentioned, and also usually has some sort of structural change associated with that transition. A second-order phase transition occurs much more gradually over a larger period of temperature. And so we go to this unique trade-off between, okay, so for magnetic refrigerant, do I want a large effect with something that could have some sort of mechanical strain involved with the structural transition, or do I want something more gradual? In any case, my research looks at developing these materials and understanding them better in order to get a sustainable alternative to commercial refrigeration. Thank you.